All right, Jeff, whenever you're ready.
All right, great. Thank you, Heather. Hi, everybody. I'm Jeff Grant. I'm the chairman of the Bowman, New Jersey Environmental Sustainability and Resiliency Committee. Thank you for joining us here this afternoon. I want to first thank all the members of the committee: Jay Greeley, our liaison, Mike Bertolo, Kevin Kelly, Nita Kovalenko, Tiffany Lewis, who's with us today, Bob McSoud, Bobby Malone, Steve Olivetti, Don Pico, Grant Salmon, and Irina Rakowski. So thank you, everybody, for your contributions to the committee. And now a call out to our sponsors, our annual sponsors. Heather, if you can put the sponsor slide up, please. Yeah, there they are, all our sponsors. All right, so our first onsite, our gold sponsor, our silver sponsor, Northeast Group and Encore Fire Protection. Bronze sponsors are, hold on, let me open this up. Apologize. Bronze sponsors are Servco Team Harvey, Spinell Electrical Contracting, Federal Business Centers, Guardian, Land Companies, Belfort Property Restoration, Colliers, Public Sewer Service, JLL, ServPro Team Majeski, and Dry Clean. And now on to our program. I'm going to introduce our first speaker. Oh, by the way, if you have any questions, there will be an opportunity to ask the questions live at the end of the program. And you can raise your hand and we'll call on you. Or if you like, during the program, you can type the questions into the chat. We'll consolidate the questions if that's possible to streamline the answers, and we'll ask them for you at the end of the program. So feel free to choose whichever way you prefer. All right, our first speaker with us this afternoon is George Leonard. He's Regional Sales Manager for Water Products for Mitsubishi Electric. He's currently serving as a Regional Sales Manager. George graduated from Rutgers University with a bachelor's degree in mechanical engineering. He has over 30 years of experience in the HVAC and plumbing industries. He currently resides in northern New Jersey with his family. So please welcome George. Take it away. Thanks, George.
Thank you, Jeff. Thanks for the introduction. Thank you, everybody, for being here. Heather, can you give me control? There we go. Okay. Thank you. So we're going to talk about heat pump water heaters today. Heat pump water heaters, just so everyone knows, they're not new products. They are new, relatively new to the US and to these markets that we all deal in, but they are not new worldwide. They've been around for a long time. But there are some differences that you need to keep in mind when we're looking at heat pump water heaters versus conventional. The first being sizing. Heat pump water heaters in general have a lower recovery rate than conventional gas-fired heaters. So what that means is that when we're designing these, we can't take the same approach. We have to consider things differently. So for heat pump water heaters, we're looking more at the number of people that are in the building and how we're going to use that, how they're going to use that water, on a daily basis. That's our main driver in determining how big these water heaters can be. And then we use storage tanks to supplement. General rule of thumb, the storage is going to be roughly 3 to 4 times more than what conventional gas-fired water heaters are going to do. And your generation plant is going to be a little smaller because we want heat pumps to run on a regular basis throughout the day. If most people on this call think about how their buildings operate, if you're familiar, your gas-fired water heaters run for a short period of time during your peak drawdown demands, and then they largely sit idle the remainder of the day. We don't want to take that same approach with heat pumps because they would be much more expensive if we were to take that approach. So what we do is we make the generation plant smaller, put in more storage to supplement, because your storage tanks are typically lower cost than the generation or the heat pump side of things. So we reduce the initial project cost by bringing in more storage, less heat pumps. And regardless of, which heat pump you're looking at using, there's a good number of them out there on the market. You want to make sure your engineer is working with the manufacturer to get that sizing assistance. Don't try to size these on your own. Don't have your team do it. Don't have your engineer do it. Lean on the manufacturers that are out there because it is sized differently than conventional gas-fired heaters. So first, we're going to take a look at one type of what's known as a single pass heat pump water heater. Single pass is one version. There's the multi-pass version that's out as well. Single pass are more efficient at higher delta T's. Single pass refers to how many times we're actually going to run the domestic water through the heat pump itself. So in the case of single pass, we're going to run it through one time. We're going to take it from that city water temperature of about 50 degrees, bring it up to your storage temperature, 140, 150, 160 in one pass through the unit. And most of those units, if not all of them, are running on CO2 refrigerant. We'll talk a little bit more about CO2 as we progress through this, but most of them are using CO2. And I know, everybody's saying, well, wait a minute, we're trying to decarbonize, we're trying to get rid of CO2. What we're talking about with these is CO2 as a refrigerant. It's not consumed, it's contained within the unit itself. And we're talking about refrigerant in the tens of pounds as opposed to tons of CO2 refrigerant, or some tons of CO2 emissions, excuse me. So don't get confused by the fact that it's CO2. We use it because it does have a very low global warming potential. It's actually the basis for all refrigerants. GWP is 1. Oxygen depletion potential is 0 on CO2. So it's the cleanest refrigerant we can potentially use. It also allows us to get COPs or coefficients of performance up to the 4.5 range, depending on the unit you're looking at. And I'm going to caution you to take that with a grain of salt. AHRI does not have a current standard for the heat pump water heater technology that's out today. They're working on it, but there's not a current standard. So whatever manufacturer your team decides to use, make sure they back it up with test data to show you what the unit can actually provide for performance. COP gives you a measure of how much energy you get out versus how much energy you put in. So if I say a COP up to 4.52, as we see here, that means for every unit of electrical energy I'm putting into it, I'm gaining 4.5 units of heat energy out that's going into the water. So that's what COP means. So the benefits of single pass CO2 based units, we can get up to very high leaving water temperatures without using electric resistance heating. CO2 allows us to get up to 176 degrees all the way down to -13°F ambient air being drawn into the heat pump. Believe it or not, there's plenty of heat in -13° air. We just have to get the refrigerant lower so we can extract that heat out of it. So most of these are available as either 208 or 460 volt units. So they'll fit into most of your buildings that you have out there, if not all of them. In general, they're going to use hot gas defrost on the condenser coil. It's going to pull, in addition to pulling heat out of the ambient air, it's going to pull that moisture out of the air as well. So it's going to have to shed that moisture off. During the winter months, it's going to have to go into a defrost cycle to get rid of it. So using that compressor and going into a hot gas defrost keeps your operating costs lower by not forcing you to turn on an electric heater. Sound levels are relatively low on these. For the most part, we can carry on conversations right next to one of these heat pumps or multiple of these heat pumps as they're running without having to raise our voices drastically. So noise generation is normally not an issue with these heat pump water heaters. You can get relatively good distances between the heat pump and the storage tanks. And we'll get into a schematic of what a single pass heat pump water heater system looks like. So that'll make more sense in a little bit. And then one of the things we're doing is taking some of the equipment out of the space. It does have to go up onto the roof. So flexibility in your roof layout is key. So consider that as your choice for which heat pump you're going to use, depending on what you want to put up on the roof of your building, if you're going to put any amenities or anything else to take up space. So again, we're utilizing CO2 as our refrigerant of choice. It's environmentally friendly, like I said, GWP of 1, ODP of 0. Big thing to know about CO2 is it's not flammable, it's non-toxic. Like I said, it's environmentally friendly, naturally occurring. I'm putting out a bunch of CO2 right now. We all expel CO2 throughout the day. So it's not something we necessarily have to be concerned about. The big drawback of CO2, if there is one that we're going to point to, is that it's a high pressure refrigerant. Now that's not a major concern because most of these units are what's known as monoblock construction. where all of your refrigerant is contained within the outdoor unit itself. We're not running refrigerant into the building. So the high pressure is not a big drawback in the sense that it's going to be anybody's going to be impacted by it if you were to experience a release of refrigerant charge from the system. But the benefits of CO2, like I said, we get that high discharge water temperature, even down to very low ambient temperatures. CO2, just so everybody knows, it's a transcritical refrigerant. It's going to stay in the vapor state throughout the water heating cycle. We don't have the phase change to contend with like other refrigerants. That's why we're able to get stable discharge water temperatures regardless of ambient air temperature. Okay, and like I said, heat pump water heaters have been around for a long time. Mitsubishi in general has been making a heat pump water heater since 2007. The CO2-based single pass heat pump water heater has been around for 17 years, just brought to the US a few years ago because we're now getting into the decarbonization and electrification movement. Before that, there wasn't a reason to bring it here. Natural gas-fired heaters got the job done, but nobody on this call is going to be a guinea pig if they go with single pass heat pump water heaters. Technology is well proven. So now I'm going to look at what a basic system looks like when we're looking at a single pass CO2 based water heater. So I don't know, can you guys see my mouse moving on the screen? Jeff, can you just give me a nod if you can see my mouse moving? No? Okay, must just be on my screen. So basically when we're looking at this, I'm going to start from the left-hand side. You see your QAHV heat pump module on the left-hand side of the wall. That's going to be outside the building. This is going to be for an air source type unit. From there, we're piping into the building to a primary secondary heat exchanger, which is shown about a third of the way in the schematic. So that's a closed loop from the outdoor unit or the heat pump to that heat exchanger. From there is where your domestic hot water is going to take over and start to be delivered to the storage tanks and then to the building. So the storage tanks are what are going to take up the space inside the building, as well as that heat exchanger and some of those components that you see right around the heat exchanger. Those are available in two configurations, either as a skidded package or as loose components, depending on which is going to work better for the actual building that we're looking at. And then over on the right-hand side, you see what's known as our swing tank, which is simply there. It's a temperature maintenance system. It's there to address the recirculation loop losses in the building. And that can take a number of forms. It can be an electric water heater. It can be a smaller heat pump water heater. It can be an indirect type tank with an injection. So, yep, that's our primary side loop. So we go from the outdoor unit to the heat exchanger. Then we get our secondary side and storage, where we're going to store the hot water until it's needed in the building, and then recirc and swing tank, where it's actually going to go out to the building. Okay, and this just gives you a little graphical view of what it looks like as far as the hot water. Your blue lines are your cold water or city water in the system. Your red lines are going to be your hot water. And then your yellow line is the recirc line coming back from the building. That's the flow you have through your building to just make sure that your furthest fixtures have hot water available at any given time. But for a single pass water heater, you don't want to bring that back to the storage tanks. We want to make sure that the blue area stays as blue as possible, while the red area stays as red as possible in those storage tanks, just to make sure that we're maintaining the efficiency on the heat pump itself. For single pass water heaters, if we were to take that yellow line and bring it back to the heat pump itself, your COP would not stay up at those high levels where it was. It would drop down, which means you're spending more on electric in order to generate the hot water. So we want to keep that yellow area separate from the red and blue that you see in those storage tanks in the center of this diagram. Okay, and again, as I said, that primary secondary setup is available in two options, either as loose components, which can be fabricated by your plumber on site in the mechanical room, or as a skid package. That's going to depend on what the project allows. how much space is available, etc. Okay, and when we get into larger buildings, we start to get into having multiple heat pump systems. We highly recommend each one of them have its own primary loop setup, as we show here. And that's for redundancy, so that if we have an issue with a heat exchanger or a pump or a sensor, you don't lose the entire ability to provide domestic hot water to the building. You're only losing a portion of the system by piping it in this manner. Okay, typically the major components you're going to get anything that's critical for operation of the system. That would be that secondary pump, the heat exchanger, the storage tanks. What we try not to do is overcomplicate and overprice things by providing too many components that the plumbers can procure from a supply house, cutting out the middleman, keep it simple, let him buy it and pass it along with his markup, as opposed to us getting involved and adding extra cost into the project. Okay, and this just shows what I was talking about before with the tank stratification and keeping your red and your blue. We want to have that center section on the left-hand tank where that yellow to orange to red is. We want to keep that as minimal as possible so that we can keep the blue as possible, going back to your heat pump, keeping your operating costs as low as possible. And then you're going to get a master control panel, which is usually BACnet compatible, can be connected into your BMS system, so you can monitor this, you can get alarming, you can know what's going on with the hot water system at any given time. So if there's an issue, you can address it before people may even realize it potentially. It also allows us to do, we don't have to do it yet, but it is CTA 2045 compatible. So if we get into a demand response situation here in Jersey, you can be ready for it. We just have to get the module from the utility and plug it in, and demand response can be handled through the control system as well. Okay, so for operation and maintenance from your the building owner and management standpoint, as I said, single pass heat pump water heaters are monoblock construction. All of the refrigerant is contained outside the building in the heat pump module itself. So we don't have to pipe to anywhere into the building, which means, in conjunction with the fact that CO2 is non-toxic and non-flammable, we don't have to worry about any refrigerant monitoring. None of those concerns exist. Even if you put a unit inside the building, you're still talking about a naturally occurring refrigerant. It's not flammable, it's non-toxic. Hopefully everybody knows that there's a refrigerant transition going on in the HVAC industry. By sticking with a CO2-based unit, you're avoiding any of those concerns and making sure that you keep your project costs as low as possible. That monitoring becomes a non-issue for these systems. Other than that, what's required for maintaining these systems? Whoops, went a little too far. There we go. Okay, so the systems can be monitored via that central control panel that you saw, or the BMS. Alarms can be sent out so that if there's a malfunction, you know about it and can handle it and make sure somebody addresses it. As far as maintaining these systems, it's really just keeping your outdoor heat pumps clear of snow and debris, and just cleaning that condenser coil periodically. Same thing as you see with air conditioning condensers today. You just want to make sure everything stays clear and operating. And then it's just the visual inspection. Check for any leaks, make sure any leaks do get fixed. Check for loose wires, the same kind of things your maintenance crew should be doing with typical air conditioning equipment today. Big thing to know, compared to gas-fired units, especially for those who are using high-efficiency gas-fired, you probably have, or you should have, costly maintenance of that burner and heat exchanger on a gas-fired system on an annual basis. That does not occur with a heat pump water heater system. So that yearly maintenance cost that you're putting in to clean those burners and clean that heat exchanger to keep it operating at peak efficiency, you don't have to worry about that with a heat pump water heater. So that's some savings from your maintenance budget moving forward. And with that, Jeff, that's
Okay.
all I have.
All right. Terrific, George. I thank you very much. And very informative. And I've got some questions in the back of my head forming. So when you get to the end,
Absolutely.
we'll have some fun with that. All right. All right. Heather, if you could please cue up Andrew's slides and I'll proceed and introduce him. So Andrew, welcome. And everybody, Andrew is the Senior Project Manager for Systems Solutions at Watts Water Technologies Applied Solutions Division. Andrew has led the introduction of many cutting-edge technologies, including the newest commercial heat pump water heating technologies. He is an ardent advocate for high-efficient, environmental friendly technologies and is passionate about applying those technologies where they can have the greatest impact. Andrew holds a BS in mechanical engineering from Columbia University, and he's currently pursuing an MBA from Wharton School of Business and is an active ASHRAE and ASPE member. So welcome, Andrew.
Thank you very much. I realize it's a very long, complicated title. The unofficial rule here at Watts is when you get a new role, it has to be a longer title than your old role. So when you've been here a while, they tend to become a mouthful. Thanks for the introduction. I'm going to talk today mostly about new construction and retrofits and what some of the strategies are. Just a quick word, if you're not familiar with this Link brand, Link is one of the brands within Watts Applied Solutions. Watts obviously offers a lot of plumbing products, but Watts Applied Solutions has a pretty broad range of products, including gas-fired water heating, gas-fired hydronics, steam-fired, electric, including the Link brand, which has our CO2 heat pump water heater, we call the Aegis water heater, as well as leak detection, water quality. So we really have a full suite of solutions. I'm not going to spend too much time on the why of decarbonization. Really, the point that I want to highlight here is there's kind of two key points. One is the goal today is to reduce or eliminate Scope 1 emissions. You know, we were having a great conversation before the meeting started about Scope 2, Scope 3, what happens outside the building, where's the utility getting energy from. What I want to focus on right now is just our buildings. Locally, what is our building doing? What does it cost to operate our buildings? And when I highlight decarbonization versus electrification, it's because we tend to use these terms kind of interchangeably when we talk about this, but they do mean different things. Decarbonization is the focus on reducing our emissions. Electrification usually assumes that the answer to decarbonization is going all electric in all cases, which is a strategy that, for instance, California has taken, and it kind of pigeonholes them in how they're going to solve this issue. So they're forced to use certain technologies and certain solutions in their buildings. Because in the East Coast, especially in New Jersey, we have targets for decarbonization, but not necessarily hard and fast rules about how to. It gives us some flexibility in how we achieve those goals. So when we talk about decarbonization, electrification, usually the first thought is let's go straight to electric water heaters, right? And they work. I'm not going to denigrate them. We sell several lines of electric water heaters. The nice thing is they're very simple, they're well established, and they're really reliable. However, there is a limit to how efficient we can get. If we start loading every building up with these electric water heaters, the demand on our grid is going to skyrocket. Plus, we know the cost of electricity can get expensive. Depending on your building, if you're retrofitting existing buildings, it may require some sort of upgrades to the available power in the building. So that's really what drives us towards heat pumps. I think George did a great job covering this, so I won't really spend any real time on it. You know, the pros of a heat pump are I can get more energy out than it takes electricity to run them. And it took me at least a year to really truly wrap my head around how that happens. It feels like it violates the fundamental laws of thermodynamics. But what's really going on here is when we do this calculation, you don't have to include the energy in from the ambient air, or in the case of a water source unit, the water, because I'm not paying for that air. I'm only calculating what I'm paying for, which is the electricity to run the unit and then the heat output from the unit. And because I can draw the box that way, you end up with these efficiencies that are 200, 300, 400%. We don't like in engineering calling something more than 100% efficient, so the term is COP, coefficient of performance. As George said, these do tend to have slightly higher first costs than some of the existing technology that we're used to. But there are ways to mitigate that. We'll talk a little bit about that in a minute. You do need a little bit of extra footprint, especially if you're comparing it to maybe like a tankless or a semi-tankless heater. And it does require storage volume like we already covered. But it does offer a huge operating savings. So this is an example system I kind of made up. We could talk about the specifics of, is this a true gallons per day? Is this what we're paying in kilowatt hours, et cetera, et cetera. I don't want to focus too much on the specifics. What I want to focus on is, this is the ASHRAE bin data from Newark. Just picked a city in Jersey. And you can see the air source heat pump water heater performance actually gets better as the temperature increases. So you're saving anywhere from 2 to 4 times the amount of energy it would take if you were just doing a resistive electric solution. So I'm seeing generally a savings of 60 to 70% over just a pure resistance electric. Now, again, I don't want to get too hung up in the details on this. It's much more effective if we're talking about specific projects, specific buildings. We can always update these types of tables, but I think it's a pretty powerful illustration of how much you could potentially save in operating costs with a heat pump. The other thing that's worth noting is, according to ASHRAE, we're really never going to see temperatures below negative, below zero in the negatives. And really, you're not going to be below 20 degrees more than, I don't know, maybe a week at a time in New Jersey. And it may be a little bit colder outside of the city. I just, picked an arbitrary city in Jersey, but, most of our heating hours are going to be spent in that area where we have really, really high coefficient of performance in heat pumps. This is typical for most heat pumps. We just saw a very similar slide. We're going to produce the heat. We're going to transfer the heat. We're going to store the heat. There's usually some sort of either backup or recirculation heating. And then we mix and deliver. Air source heat pumps. This is kind of what it might look like in a building. These are probably the most common solution because everybody has air, right? There's air outside the building, so I don't have to worry about where's the source energy coming from. Typically, they get put on a roof, they get put outside the building on grade. Sometimes I do see them in parking garages, which is kind of like an indoor-outdoor area that does protect against some of the colder conditions. That's very common in the Pacific Northwest. I see a lot of that in like Washington and Oregon. If you're sizing the system to run purely off of a heat pump, you're going to size that heat pump for the coldest day of the year. But like we just saw with the bin data, most of the year, you're actually going to be operating much, much warmer conditions than that. So the system may end up a little oversized most of the year. There are ways around that we'll talk about in a second. There is a slight cooling effect around the unit. People sometimes ask, can I use that for air conditioning? It doesn't really work that well because you're only going to be cooling the air when you're actively making hot water. You're not going to be cooling it to a specific temperature. So typically, unless it's indoors, we kind of ignore that effect. And this is somewhat easier in new construction just because you can lay out the footprint you need. But it's not to say it can't be put in retrofit. We have plenty of retrofit projects as well. So what I think I really want to focus on here is how do we retrofit existing buildings? Because there are challenges to retrofits, especially if it wasn't designed around something like a storage solution. So if it was retrofitting non-storage, space is probably the #1 concern. Space for the tanks. If it's an air source unit, space for the heat pump itself, running the piping between the two. But there are a couple of options to both help reduce the footprint, help reduce the first cost of the system, and provide a little bit more redundancy. And that is with hybrid systems. And when I say hybrid, that could be hybrid heat pump and electric. It could be hybrid heat pump and gas. We've actually got hybrid heat pump and steam systems, which are kind of interesting. And those systems, we'll look at a couple of examples. Really, the goal is to let the heat pump do 90% of the work, and then the backup system does the next 5 or 10%. So when you design a system, instead of designing for that 0 degree or -4 degree day, let's design for maybe 30 degrees or 30 degrees and up. That way we're catching 90% of the annual heating load, and it's only that 10% that we really need a backup system for. It's a really great opportunity to reuse existing equipment. So if you have something that's maybe nearing end of life, you think you may have only a year or two left on that gas-fired equipment, let's kind of demote that in a sense to backup. And now instead of running for 2 years at 8,000 heating hours in a year, I can now run for 10 years because I'm only running them for 40 hours a year. That's a really great opportunity. Helps reduce the first costs as well, spread the cost of the project out because I don't need to replace that backup heat for a little while, provide some extra redundancy. Really the biggest challenge there is a lot of times where I see these projects implemented, it's because they've already decided the answer is all electric, it has to be all electric. And we can provide those systems, you just provide an electric water heater. But in an area like New Jersey, where we don't have that mandate from the state to go all electric, you do have flexibility to put in some sort of combination system. So again, going back to this diagram of produce, transfer, store, backup, deliver, we could put backup heat in one of these tanks that already exists, right? So instead of just a plain storage tank, we could potentially make that an electric storage tank. Or in the recirc tank, the same thing. It could be gas, it could be electric. There's a lot of opportunities in here. So this is an example system where there's something we're actually working on right now. I can't tell you where it is because I haven't been given permission to use the building's name yet. But what we're doing is we're taking an existing system with a storage tank and 2 gas-fired water heaters, and they wanted to add heat pumps with the understanding that the heat pump is not going to cover the entire load. The heat pump is only going to be capable of covering part of the load, and they're fine with that because their goal isn't to remove the old equipment, it's to just reduce the emissions in this building and reduce their operating costs. So it's a little bit hard to see what's going on here, but if you look at this diagram, you have everything in the existing system in red, everything in the new addition to the system in green. It's the heat pump. The key here is that the cold water supply is only feeding the heat pump system, and I didn't highlight it, but the mixing valve as required. What this means is if there's a draw on the system, all of the heat comes from the heat pump through that existing tank and out to the building. The heat pump is the primary source. Only if that heat pump completely runs out, that tank completely gets cold, and the heat pump capacity is outstripped, only then will the gas-fired system come back on. So what we've really done here is kind of designed right into the plumbing, the control and the energy savings. Even if the gas-fired heaters come on, the heat pump is still going to continue to operate. So it'll still always be the primary heat source. And you're always getting that benefit of the higher performance in the heat pump, even if you're also running the gas-fired at the same time. So that's to say, as a whole system, you've made a big impact in reducing your emissions and reducing your operating costs. But all we've really done is add a little bit of redundancy to an existing system. The other opportunity that I mentioned earlier was, let's change the design day. So instead of designing equipment for 0 degree operation, knowing that we're going to very rarely be there, let's design it for maybe, I think in this case, I said 25 degree. Oh, that's what I did. I said, let's call it the 94% we'll cover 94% of the year. We'll let the other 6% be on the backup system. So let's fix the backup system. Let's call it the resistance electric. We'll fix the COP of 1. Really, it's like 0.98, but I'm rounding up here. I'm going to get the same performance out at those low ambient temperatures that I would in a resistance electric solution. So my output required is the same as my input required, but everything above that, now I'm realizing the performance benefits of a heat pump. The difference between this and the energy savings we looked at 5 or 6 slides ago is maybe 5–6% of the kilowatt hours per year. And then I think you're in the comparison here, it's like $1,500–1,600 difference, not even. Now, again, I picked a random system. I picked a somewhat educated kilowatt per hour. You may be getting more favorable rates than that. But the point I want to make here is if we're designing for, let's say, 90% instead of 100%, I'm still realizing most of the benefits of that system without having to go crazy and do all this extra work and provide. Maybe I'm reducing the amount of heat pumps by 1. Maybe I'm allowing it to run on an existing backup system. There's a lot of potential benefits here. And the other thing that I want to mention is, we've been talking about air source, air source, air source. Don't forget about water source as an opportunity. If you have geothermal loops, if you have building cooling, there's an opportunity to use that as your heat source instead of the air. There's a lot of benefits here, especially in the Northeast, because we don't have to worry about what the winter temperatures are doing to our ambient conditions. It's pretty much going to be the same performance year round, especially if it's geothermal. Process applications are another great application. I see it more often in chilled water loops, larger buildings that always have some sort of cooling load. The benefit here is I'm sending water from the chiller cold, returning it to the chiller warm, and before I do all the work on the chiller side, I'm actually transferring some of that heat through the heat pump into my domestic hot water plant. It basically means I'm getting a performance boost on both sides. I'm getting the high efficiency on the water heating and improving the performance of my chiller, reducing the load on my chiller plant. When we talk about the performance, we don't really call it COP because it's kind of unfair adding both sides. We usually call it total energy ratio, or some people call it integrated COP. But really the only challenge with this design is that you have to make sure that your plumbing and your mechanical teams are all communicating with each other. The nice thing about this in retrofits is you can see a water source unit is much, much smaller because I don't need those very large air coils to capture heat at cold ambient temperatures. So they tend to be much, much smaller heat pumps and a little bit easier to fit into existing buildings. And then just one quick word on maintenance. I know George already talked about that a little bit. Because these systems are, they're all sealed appliances, they're all that monoblock construction. Everything's sealed. You don't have to worry about really the refrigerant side on site. So you're not going to require specialized operational training for site staff. The maintenance is pretty low impact, cleaning an air coil here or there. Maybe if you check the oil on the compressor, that's about the only other maintenance item I can come up with. And then we talked about it a little bit, but both the Mitsubishi and the Lynx system are all CO2 based refrigerant. It's all R744. The nice thing is we consider it future proof. Things like 410A and 134 are currently in the process of being phased out. You can still buy them, you can still install them new, but it's going to be much, much harder to get a hold of them in the future. So even though the system cost now may not be as high, if you have a maintenance need to replace that refrigerant in 5 years, it's going to be very expensive because it's going to be very hard to source. There are some transition refrigerants that are currently available, but will start to get phased out in the future. Everything that's a natural refrigerant, propane, CO2, ammonia, is considered future-proof in the sense that the EPA isn't really looking to phase those out. So you're never going to have to worry about availability in the future. I know that's a little forward-looking, but it does come up in conversation. I believe that was all I had. So thank you very much, and I'll turn it back over to you. Jeff. Jeff, you're still muted.
Yeah, that's happens a lot. Yeah, okay, Andrew, thank you very much. Very, very informative, great slides, appreciate it. And for you, I've got some questions as well, so stand by. All right, next on our speaker bench, our speaker roster is Tiffany Lewis. She's going to be talking to us about incentive programs in general, and hopefully give us some guidance on how it might apply to electrification of domestic hot water. It's kind of a gray area, but I'll let her struggle with that one on her own. I'm not going to speak for her. Tiffany is a member of the Bowman, New Jersey Energy Sustainability and Resilience Committee. She's a successful results-driven leader with 17 years as a professional project manager, skilled in strategic planning and problem analytics and resolution, both as a team member and as an independent consultant. Her focus empowers customers and contractors, and I would add consulting engineers to that, for informed decision-making to achieve their efficiency goals. She provides concierge support and service, helping assess potential projects and identifying appropriate incentive programs to maximize customer capital application. So please jump in, Tiffany. Thank you.
Thank you, Jeff, and good afternoon, everyone. Pleasure to be here again. As Jeff mentioned, so I am here today on behalf of JCP&L, which is what my slides speak to. TRC has the great pleasure of administering many of the state's commercial energy efficiency programs. So I do have a high-level understanding of how to navigate these programs. First, I wanted to go into highlighting the benefits of participating in these programs. That being that, of course, it helps to reduce carbon footprint, positively impact the environment, improving on environmental health, as well as providing you with safety and comfort while saving your business energy and, of course, money. So energy efficient equipment like the hot water heaters, both for domestic and commercial spaces, have ways to save energy. So you can utilize the programs, the electric utility programs, where there are electric savings, and then you would apply through your gas utility company where there are gas savings. So the full portfolio that is being shown right now is housed within all of the utility companies' commercial energy efficiency programs. It includes a prescriptive and custom pathway for single measure upgrades, and some select equipment can go through the instant discount program, which prevents for any paperwork for the customer or the contractor. You purchase the equipment, receive the discount, you make the installations, and the supplier is responsible for taking care of the paperwork. But if you're looking for a more comprehensive approach to energy efficiency, there is the small business direct install program, which is not just for small businesses, but is for facilities that average 200 kilowatts or less within a 12-month period. If you exceed that amount, then you would go the route of the energy management program. And typically for the MUSH sector, municipalities, universities, schools, and hospitals, you can go the engineered solutions pathway, which allows for you to look at multiple sites with multiple utility account numbers as one project if it is owned by one entity. So this slide just gives you a snapshot of the equipment that can go the prescriptive pathway. And it was briefly mentioned today that compressed air systems and more standardized equipment like boilers and chillers also go the custom route. It was also mentioned that building management systems can also help improve the efficiency of certain equipment, and because there's energy efficiency savings there, it can also be receive incentives for a building automation system or a building management system. This would go the custom route where you receive dollars per kilowatt hour saved. And then the application process is pretty straightforward. There's always a list of contractors who are considered either program allies or trade allies, that term is used interchangeably, who can support you with submitting applications. The prescriptive programs for the utility companies do have a 180-day look-back feature if you have recently done any upgrades. Custom projects do require pre-approval, which means you have to apply before the equipment is purchased or installed. The contractor can support you with navigating everything moving forward, including pre or post inspections where projects are selected randomly just to ensure appropriate participation in the programs. Projects typically have 90 days for installation once the customer has accepted the offer for the incentive amount that's being provided. And then you receive a check at the end of the project. It's very straightforward. As mentioned, each utility company does have a list of contractors that you can work with, or a group of outreach account managers like myself, which help you with navigating these programs, as well as supporting you with assessing your project needs. Tried to keep that very short and sweet because what's really important to know is that there are a team of energy advisors and outreach account managers that are here to support you. There is money available through incentives for retrofit projects for existing buildings, as well as from the state for new construction projects. Where there are energy savings, there is money available for those facilities that have an investor-owned utility company that is available, providing them with service. Thank you for your time today, and please reach out if you have any questions.
Great. Well, thank you, Tiffany. And just having worked with the utility companies and Tiffany, I can tell you we're at the Q&A period, and I'm going to make a comment before we kick off with the questions. And my comment is that there's very generous incentives that are available now, and the incentive programs are going to be even more generous starting in January of 2025. And we look forward to those programs and how they might fit into helping leverage capital if somebody wants to retrofit an existing hot water system with this new technology, or new construction, how to help leverage new construction capital for the same goal. So thank you, Tiffany. All right, we got a few minutes left, and I wanted to find out from George. It's kind of a general, not specifically just question relative to the domestic hot water heat pumps, but the whole concept of electrification in general. We've got, institutions like Princeton University, for example, that are putting in geothermal wells or geosourcing wells, and they're using that geothermal well heat source, heat sink, to store heat in the summer and to extract heat in the winter, and pipe that to existing radiation systems in their building. The problem they have turned out not be a problem, but you can generally only get up to about 120 degrees with traditional HVAC equipment, high head chillers and so forth. I'm intrigued, George, that these CO2-based systems are able to get up to, I think I heard you say 176 degrees, which is terrific, where that can be a viable heating source for hydronic systems. Do you see any future where this technology is going to be scaled up to be able to provide HVAC heating for folks that want to decarbonize and do it by electrifying? George, you're muted.
Unmute myself. Can you hear me now?
Yeah.
Excellent. So that's a great question, Jeff. One we get frequently because we do promote that the units can deliver such high water temperatures. The drawback, however, is that CO2 as a refrigerant is only efficient when we're looking at a very high delta T, so 80, 100 degree delta T. Whereas when you're looking at comfort heating conditions, you're in a 20, maybe a 40 degree delta T. So the COP, of a system like that is not going to get you up to those 4.5, 5 levels. It's going to be more in the 1.5 range for COP. meaning it's really not that much more efficient than just running an electric boiler at that point. So, so that's the drawback of CO2 is that it's really only ideal for large delta T like a domestic hot water application. Now, we've been kind of kicking around the idea of storing the water at an extremely high temperature,
Mhm.
160, 165 degrees,
Mhm.
and kind of using that possibly through a heat exchanger to deliver 140 degrees to the radiant flow, to the fan coils and such, and then still have close to 140-degree water, because that's our threshold for domestic hot water. We want to make sure we're maintaining 140 degrees or higher in those storage tanks due to
Mhm.
Legionella concerns. So we can't give up too much of the heat and drop those tanks down to 120 degrees. Then we're in the Legionella growth period as opposed to the killing period. So we'd run into concerns there. So it is a tight window where we might be able to make it apply. It's going to be the exception rather than the norm for sure.
All right. So there's still a window of possibility with some added on features to make it work.
Yeah,
but
very small window.
Yeah. All right. Well, that's the challenge that engineers and environmentalists have ahead of us, is to utilize existing hydronic coils and radiation systems in an electrified hydronic heating world. Very, very difficult to do. Okay. All right. Well, thank you. All right. And then Andrew, I have a question for you about space requirements. Your diagram showed, what on the surface appeared to be, a fairly robust sized mechanical room for the 3 storage tanks and of course the heat pump equipment on the roof. I mean, in terms of a typical central plant system with hot water boilers and chillers and so forth. I mean, what kind of square foot or what kind of percentage are we talking about that engineers will need to allocate for domestic hot water heat pump systems? Newer.
Yeah, it's a tough question to answer in the abstract because it's so dependent on building loads and that balance between how much is storage versus how much is recovery. Generally speaking, the heat pumps themselves, if it's a water source, it's like 3 feet, 3 feet by 3 feet. The tanks, you're probably looking at, I'm trying to remember tech data sheets off the top of my head, probably looking at like maybe 15 to 20 square feet per tank and maybe 2 to 3 tanks per installation, plus a little bit more for piping and heat exchangers. So it's a decent size, but there's also a lot of opportunities to be flexible. The systems that I showed were just, one example of, hey, we picked these tank sizes to do a rendering.
Okay.
We've definitely done systems, especially in retrofits, where we built a series of half a dozen 190-gallon tanks because they fit through a 3-foot door. And we just squeezed like half a dozen or a dozen tanks through a small door. And because you're piping everything in series, it doesn't really matter if it's 2 tanks or 3 tanks or 4 tanks. It actually kind of helps the stratification a little bit. So definitely in the retrofits, there's opportunities to be flexible in how we approach that storage volume and that footprint.
Okay. All right. Fair enough. But it certainly is a consideration, but it doesn't sound like it's going to be that big a deal. Mechanical rooms generally have enough space to be able to fit these things in. If there's well designed, they're usually designed to have the future built in mind, so they can be things can be added to them and brought into them. That's great. All right. I did want to make one observation, by the way. Very good degree day analysis, and then doing the 94% design I thought was very, very ingenious. It's very expensive to design for all those degree days all the way down to 0. Just an observation on behalf of everybody that might be listening, and what that means if everybody in the state does these 94% designs and then uses electric resistance heat for the other 6%. If everybody does that and we hit one of those, 0-degree days for a couple of days, and we've had them in New Jersey, we will have an incredible load on our grid that I question whether with all the sustainable equipment we're going to have, it's going to be wintertime, not a lot of solar is going to be available. wind doesn't blow quite as hard in the wintertime, it's going to be pretty tough to handle that load when we get out to those low temperatures. So just be mindful of that. There could be all kinds of grid repercussions to that. All right, my last, well, we're running out of time, but I would just say, I'm interested in Tiffany's contribution as we, get into the new incentives. And we're probably going to have a program, we're planning a program early next year to update everybody on the new incentives. It's called Triennium 2 coming out early next year. And hopefully by that time, we'll have some idea on how we can help advance your technology, gentlemen, with state help. I mean, the goal of the state is to begin eliminating natural gas in existing systems in 2030 and to outlaw natural gas in new systems next year. So, as the state goes down its energy master plan policy, I think your technology is going to become more and more relevant, and then the need for financial incentives to help leverage capital to make them happen is going to become more and more important. So hopefully, Triennium 2, the next incentive program, will help advance that, and we'll update everybody, with our next program, and Tiffany will certainly be part of that as we formulate it, late this year and early next year. So, all right, any other questions for the folks that are here with us? All right, I'm stealing the floor from everybody. Okay, all right. With that, I want to thank Heather for being the force in the background that keeps things moving, keeps our programs flowing. Thank you, George, and thank you, Andrew, for your time and expertise. Two very good presentations, very much appreciated, and you too, Tiffany, for your presentation and being there to backstop us or to support us with the financial incentives and the people to help bring those financial incentives to life. So, all right, thank you, everybody, and I look forward to seeing BOMA members at the upcoming Toby Award meeting next week, and look forward to seeing you all at future energy sustainability resiliency webinars. Thank you all. Have a good day.
Thank you, Jeff. Thank you, everybody.
Thank you, everyone.
Yeah.
Have a good day, everyone. Thank you.